Take 5 seconds and think back to 1971. What world-changing event comes to mind? Was it the end of the Bretton Woods system? The first microprocessor? The birth of the modern digital age? No, none of those. In 1971, something far more unsettling happened quietly, almost unnoticed by the public. For the first time, black holes were confirmed to be real. Not mathematical tricks, not theoretical monsters, but actual, physical entities embedded in the fabric of the universe. At the time, this seemed like a technical victory for astrophysics. Yet the deeper consequence was far stranger. Black holes were not defined by what they were made of, but by what they erased. Regions where matter, light, and even information appeared to thin toward nothingness. This discovery forced an uncomfortable shift in perspective. What if the universe is not primarily shaped by what exists, but by what is missing? As the cosmos expands, it does not fill itself with more matter. It creates ever-growing regions of emptiness. Vast cosmic voids now dominate the universe by volume. Stay a little longer, because once we understand how nothingness became the most influential presence in the cosmos, we may realize that the universe does not expand into space at all. It expands by hollowing itself out. Emptiness is not the only place where the universe hides. Sometimes it hides in plain sight, inside objects so extreme that almost everything about them has been stripped away. Think about how much it takes to describe something ordinary. A coastline, a thundercloud, the surface of the moon, pitted with impact scars and dust. In principle, to describe it exactly, you would need to specify the height of every crater rim, the shape of every grain, the position and motion of every molecule and photon. The more structure there is, the more numbers you need. Complexity demands description. It resists being compressed. Physics gives this idea a technical name: information. Not information as in gossip or news headlines, but as a measure of how many different ways a system could be arranged while still counting as the same thing. A calm lake and a stormy sea may contain the same amount of water, but they differ in their patterns. That difference is information. Now place beside that messy, detailed world the most extreme object we know how to describe: a black hole. It can swallow stars, distort time, and reshape the trajectories of light itself. It can sit at the center of a galaxy and silently govern its surroundings for billions of years. And yet, according to our best theories, the outside world only needs a tiny checklist to describe it. 3 items: its mass, its electric charge, its angular momentum. Mass is the easiest to picture. It is a measure of how much stuff has fallen in, or more precisely, how strongly the black hole warps space-time around it. The higher the mass, the deeper the gravitational well, the harder it is for anything to escape. If you think of gravity as the curvature of a fabric, mass is how sharply that fabric is pulled down. Electric charge is more subtle. It counts the imbalance between positive and negative charges that have fallen in. In practice, black holes in astrophysics are expected to be almost perfectly neutral, because surrounding plasma and radiation tend to cancel any net charge quickly. But in the mathematics of general relativity combined with electromagnetism, charge is allowed, and it must appear in the description. Angular momentum is the measure of rotation, how much the black hole is spinning. It is not just how fast the surface would move, because a black hole has no solid surface in the usual sense. Instead, it measures how much twist has been locked into space-time itself by the collapsing matter. A rapidly spinning black hole drags nearby space-time into rotation with it. This dragging is called frame dragging. a consequence of general relativity where the very stage on which events occur is forced to rotate. 3 numbers. For an object that can change the fate of a galaxy. The details of what fell in do not appear in this simple summary. Whether the black hole formed from a cluster of stars, a collapsing gas cloud, or a series of mergers does not matter for its external description. Whether it has consumed planets, dust, or radiation does not change the checklist. Once enough matter crosses the critical boundary and the black hole settles down, only mass, charge, and spin survive in the equations that describe its exterior. This is not how we are used to thinking about objects. A human life is full of specific events, memories, choices. We instinctively feel that erasing those details would erase the person. A forest fire may reduce a landscape to ashes. But we still distinguish one forest from another by history, by what grew back, by traces that remain. In our everyday world, the past leaves marks. Black holes suggest something colder. They offer a picture of reality in which many different histories converge to the same end state. A star that lived quietly before collapsing and a star shredded by violent collisions on the way down can produce the same black hole. For the distant universe, the route does not matter. The result is identical. In physics, language, many initial configurations flow toward the same final description. The rich, branching tree of possibilities narrows into a single trunk. All that complexity, all those differences, crushed into 3 parameters. This is where the unease begins. If information is tied to distinction, and distinction seems to vanish, what exactly has been lost? Are these details simply hidden, unreachable behind the boundary of the black hole? Or are they gone in a stronger sense? Deleted from the universe? The question is not only technical, it brushes against something we rarely say aloud. We want the universe to remember. We want causes to leave traces. We want stories to matter beyond their ending. The idea that entire histories could be compressed into a handful of numbers feels like an insult, not just to matter but to meaning. Yet from the perspective of an outside observer, the simplification is not optional. It is enforced by the mathematics of general relativity. Once a black hole has formed and settled, its gravitational field depends only on those 3 quantities. No measurement of orbits, of light deflection, of time dilation outside the horizon can extract more. However you probe it, whatever instruments you build in theory, you keep running into the same wall of simplicity. Paradoxically, that simplicity is what allows black holes to behave like engines. An engine, in the broad physical sense, is a system that can undergo processes again and again, transforming energy in a predictable way without falling apart. Think of a piston, a turbine, a water wheel. They need to be robust. Their behavior must be largely independent of the tiny details of each fuel molecule or each swirl of water. If they were as sensitive as a sandcastle to each grain of sand, they would dissolve. A black hole, stripped of almost all individuality, is robust in exactly that way. You can keep feeding it matter. And as long as it does not disrupt the large-scale structure, the external description shifts smoothly. A little more mass, a little more spin. The object does not need to know what. Specifically, it is eating. It only needs to deepen and twist space-time in response. Seen from far away, this is a kind of mercy. You do not need a universe worth of information to predict how the black hole will curve light or steer orbits. The rules are compact. The outcome is simple. Seen from close up, at least in imagination, it is something else. A reminder that the universe may accept countless detailed stories and return only a few summary numbers, that the ledger in which events are recorded might be surprisingly short. The idea of a perpetual engine begins here. In this uncomfortable compression, an object so extreme that it demands almost nothing to be described, yet can influence its surroundings for cosmic timescales. It does not run on clever design. It does not remember the shape of the things that built it. It persists because the laws that govern it are indifferent to detail. We stand outside, unable to see in, watching an object defined more by what it has forgotten than by what it contains. And the next question is unavoidable. What exactly is the boundary that allows this forgetting to happen and hides it so completely from view, from far away? The boundary feels abstract, like a line in an equation. Up close, at least in thought, it becomes something else, the place where a story still visible from the outside simply ends, while the events inside continue without witnesses. We give that boundary a name, event horizon. The phrase sounds like marketing, but it is literal. It is the surface beyond which events can never affect an outside observer. Not because we are too clumsy to detect them, not because our telescopes are not advanced enough, but because the structure of space-time itself forbids any signal from escaping. To see why, it helps to start with something simpler and more familiar: escape. On Earth, escape means climbing out of a gravitational well. Throw a ball upward. If it is slow, it arcs and falls back. If it is faster, it climbs higher before returning. There is a particular speed at which it would just barely fail to return, coasting farther and farther away, slowed by gravity but never dragged back. That special speed is called the escape velocity. For Earth, that speed is a little over 11 kilometers per second. In words, in each second, the object must cover more than 11,000 meters upward, ignoring air resistance, to avoid falling back. Rockets do not leap straight to that speed, but over time they build up the required velocity. Now imagine increasing the mass of the central body while keeping its size fixed. Gravity strengthens. The escape velocity rises. There comes a point when the required speed reaches the speed of light in vacuum, which is about 300,000 kilometers per second. According to relativity, nothing with mass can be accelerated to that speed, and nothing can outrun light itself. Beyond that threshold, there is no hope of getting out once you are too close. If you keep compressing matter, not only does the escape velocity at the surface reach the speed of light, but the very nature of the surrounding space-time changes. The equations of general relativity describe this transition in a precise way. At a certain radius, the geometry rearranges itself into a one-way surface. That radius, for a simple, non-spinning, uncharged black hole, is called the Schwarzschild radius. For a black hole with the mass of the Sun, that radius would be about 3 kilometers. Take all the mass of the Sun, compress it into a sphere whose radius is roughly the length of a small city, and you have crossed the threshold. The event horizon is not a material shell located at that radius. There is no crust, no membrane made of atoms. If you were falling freely toward a large enough black hole, you would not feel a sudden jolt as you crossed it. No impact, no bright flash. For a supermassive black hole, tidal forces at the horizon could even be modest enough that a human body would not be torn apart immediately. Locally, the crossing feels like any other moment of free fall. The difference is global, not local. In the language of relativity, what changes is the pattern of possible paths through space-time. Think of each event in the universe as a point in a vast four-dimensional fabric, with time as one direction and space as three others. At each point, there is a set of possible future directions in which you could move, limited by the speed of light. This set is often pictured as a cone, the light cone. Inside the cone lie all paths a physical object could follow into the future. Outside are paths forbidden by relativity, far from a black hole. The light cones tilt only gently, and many of their future paths extend outward, away from the mass. A rocket or a beam of light launched in those directions can, in principle, escape to distant space. As you approach the black hole, the cones begin to lean inward. Gravity is not just pulling you, it is reshaping what counts as a possible future. At the event horizon, the light cones tip so far that the only future-pointing paths available to you point inward. Even a ray of light, which always moves along the edge of its light cone, finds that its possible future directions all lead deeper toward the center. Crossing the horizon is therefore not like stepping into a stronger wind. It is more like stepping into a region where time itself is aimed inward. Causality is the simple idea that causes come before effects, and that influence cannot jump arbitrarily from place to place. In everyday life, this is obvious. You flip a switch, then the light turns on, you speak, then someone hears you. In relativity, causality is encoded in those light cones. You can only send signals along paths that stay within them. When all such paths from a point fall inward, any message launched from there must sink further into the black hole. No possible sequence of actions can reverse that. No amount of fuel, no technology, no plan. It is not a problem of strength, but of geometry. This is why the word black is used. It does not describe a color in the usual sense. It encodes a prohibition. The hole is black because no light emitted at or inside the horizon can propagate to the outside universe. Whatever happens within that boundary, it will never brighten a telescope on Earth. The interior becomes a region of events that are absolutely elsewhere. The event horizon is therefore a kind of mask, not a physical mask wrapped around an object, but a boundary in space-time that separates what can influence us from what cannot. Everything about the interior evolution of matter and fields inside the horizon is, as far as outside observers are concerned, sealed away. All we are allowed to know about the black hole, if we stay outside, is encoded in the way the horizon itself curves and moves. Here a quiet tension appears. From the outside, only the mass, charge, and spin matter. Those parameters are read off from the gravitational and electromagnetic fields at large distances, and they are enough to predict the behavior of orbits and light rays. Yet the same laws of physics that prevent signals from escaping also guarantee that something continues to happen inside. The story does not stop at the horizon. It merely stops being exportable. There is an unsettling parallel with our own limits of understanding. We can see the consequences of many processes, but not their interiors. We infer the presence of a mind from words and actions, but we do not see the inner stream of thoughts. Here, the analogy is only loose, and it should not be taken too far. But the shared pattern is hard to ignore, a surface beyond which direct access is denied, leaving only indirect clues. Another subtlety: the horizon is not fixed. As the black hole absorbs matter or radiation, its mass increases. For a non-spinning, neutral black hole, the radius of the event horizon grows in proportion to the mass. Feed it gas, stars, even the faint glow of the cosmic background, and the boundary expands. The region from which no return is possible swallows more of space-time itself. This growth is not spectacular. There is no visible shockwave. The surface simply adjusts. Because the horizon is defined by the paths light could trace, it is also defined teleologically, by the fate of light far into the future. To say that a point lies inside the event horizon is to say that any light emitted there will fail, even given infinite time, to escape to infinity. This means that the horizon is not something you can locate with perfect certainty using only local measurements. Its definition relies on the entire future history of the spacetime. There is something quietly disturbing about a boundary whose existence is tied to what will happen, not just to what is. For a traveler falling in, the experience depends on the size of the black hole. Near a stellar mass black hole, the tidal forces near the horizon are intense. Gravity at your feet differs sharply from gravity at your head, stretching you in one direction and squeezing you in others. Near a supermassive black hole, those gradients can be gentle at the horizon, you might drift through without immediate drama, only later encountering regions where space-time curvature becomes violent. In both cases, the external verdict is the same. Once inside, you cannot send any information back. From the standpoint of the outside universe, the horizon is therefore the only part of the black hole that really matters. It is the interface that turns in falling matter into changes in mass and spin, the surface whose area connects to entropy, the boundary that radiates in the quantum picture. Whatever lies beyond is necessary for the full solution of the equations, but irrelevant to anything that can influence us. The engine, as far as we can access it, is all surface. This perspective is deeply impersonal. The horizon does not care what crosses it. There is no discrimination between the fall of a photon and the fall of a planet, between a cloud of hydrogen and the collapsing core of a star. Each simply contributes to the same global quantities. From outside, one more unit of mass is one more unit of mass. One more increment of spin is one more increment of spin. The boundary registers the change and moves on. So we are left with an object whose defining feature is not an interior but a limit. A limit on what signals can escape, on what histories remain visible, on how much of reality we are allowed to reconstruct. The point of no return is not a cliff in space. It is a horizon in possibility. Beyond it, the universe continues without us. And yet, when we look at galaxies across cosmic distances, we do not see dark holes eating silently. We see, in many cases, violent brightness, cores that blaze with more light than the combined stars of their host galaxies, regions where matter near the horizon shines with almost unbearable intensity. Something about this boundary, built to trap and erase, is surrounded by light. The question that waits is simple and sharp. If nothing can escape from within, why does the edge glow so fiercely? That brightness is not a confession of what lies inside. If anything, it is a flare at the boundary of silence. A final signal sent just before the universe stops telling us what is happening. The silence continues in another way, deeper and stranger. When physicists say that a black hole has no hair, they are not trying to be poetic. They are trying to describe a kind of brutal uniformity. In everyday language, hair stands for details, quirks, irregularities. The phrase "no hair" means that in the mathematics of general relativity, a settled, isolated black hole has no identifiable features beyond those few parameters we already met: mass, electric charge, and angular momentum. Imagine throwing different things into the same black hole. A star with planets, a cloud of gas, a stream of dark matter, whatever that ultimately turns out to be. You could add a swarm of comets, a ring of dust, even a carefully engineered arrangement of matter carrying information like a cosmic hard drive. At first, the combined object would be messy. Its gravitational field would bear the imprints of all those moving parts. The horizon would ripple. Space and time around it would wobble. But general relativity predicts that such disturbances do not last. Ripples in space-time propagate away as gravitational waves, gentle or violent, depending on the process. The black hole rings like a struck bell and then calms. Over time, the oscillations decay, carrying excess information about the initial chaos out into the wider universe. What is left behind is a simpler configuration, a black hole completely described from the outside by mass, charge, and spin. The no-hair statement is this: once the ringing has faded, black holes of the same mass, charge, and spin are indistinguishable to an external observer. It does not matter whether one was born from a single collapsing star and the other from many mergers. It does not matter what complicated distributions of matter once surrounded them. If the global parameters match, the external geometry of spacetime is the same. In more familiar systems, we expect history to matter. A tree's rings record seasons of drought and abundance. A scar on a surface remembers an impact. Even in physics, many systems carry memory. A magnet remembers the direction in which it was aligned. A crystal remembers how it cooled. In principle, if you could access all microscopic details, you could reconstruct much of what happened before. Black holes push against that intuition. The theory suggests that many possible pasts funnel into the same future state. From the viewpoint of the outside universe, those different stories share a single ending with no visible remainder. The fact that a complex, branching history can terminate in such a compressed description is not just a technical detail. It nudges against the way we want causality to feel. We tend to treat uniqueness as sacred. Lives, events, trajectories are supposed to differ in ways that never fully overlap, even when two stories resemble each other. We resist the idea that they could become literally interchangeable. The no-hair result hints at a cosmos that does not share that reluctance. Given the right conditions, it is willing to let entire histories collapse into the same three numbers. The mechanism behind this is not mystical. It is dynamical. When matter and fields fall toward the forming black hole, any irregularities in their distribution contribute extra structure to the gravitational field. That structure is unstable, like a perturbed drop of liquid seeking a spherical shape. The space-time around the black hole relaxes toward a simple, stationary form. Deviations radiate away. The final solution is one of a small family of possibilities, fixed by the global charges. Hair, in this technical sense, would be any persistent feature beyond that small set. A long-lived bulge, a frozen lump, a memory imprinted on the horizon that could be read externally. According to the classic theorems of general relativity, such extra features are not allowed for black holes in ordinary conditions. The horizon cannot support those kinds of scars. Whatever tries to remain is either radiated away or swallowed irreversibly. There is a cruel efficiency in that. Not the efficiency of a machine designed to maximize power output or minimize waste, but the efficiency of equations that admit only a few stable solutions and discard the rest. It is as if gravity, when pushed to an extreme, refuses to catalog every detail and instead insists on a short summary. From the perspective of engines, this stripped-down nature is exactly what makes black holes useful, because their external behavior depends only on a small number of parameters. They can serve as predictable sinks of energy and momentum. Matter spiraling toward them does not need to be arranged in a precise pattern. The details of each infalling particle do not derail the overall process. The system is indifferent to the fine print. For the same reason, black holes are unsettling mirrors. They suggest a world in which many differences we care about do not register at the deepest gravitational level. All the textures and narratives that seem essential to us look from far enough away, like slight variations in how quickly a horizon grows or how fast it spins. The universe keeps a record, but the record is sparse. To be clear, not all information is obviously gone. Some of it escapes in the gravitational waves and radiation emitted during formation and mergers. Observatories like the instruments that first detected gravitational waves are, in effect, listening to the dying echoes of those complexities. Each observed signal carries clues about the masses and spins involved, and about the dynamics of the event. But once the ringing is over, once the final black hole has settled, the remaining object is simple again. Whatever detailed pattern once existed is no longer present in the external field. This raises the longer, unresolved question of whether information is truly destroyed or merely hidden in ways we do not yet fully understand. That problem deepens once quantum mechanics enters the picture and returns later in a sharper form. For now, within classical general relativity, the message is plain. The outside description forgets. You can read this forgetting as a limit of knowledge. a line beyond which observers cannot reconstruct the past. You can also read it as a statement about reality itself, that at least some layers of difference are not fundamental, but emergent, vulnerable to being stripped away under extreme conditions. The theory does not tell us which interpretation is more correct. It only tells us where the prediction is robust. What remains, then, is a kind of mechanical humility. Above a certain threshold of collapse, the universe stops caring about particulars. Mass is mass. Spin is spin. Charge is charge. A system that once contained stars, chemistry, perhaps even life, is replaced, in the outside description, by a blank object with a handful of numbers attached. The engine is built out of what used to be stories, and it does not remember them. And yet, despite this indifference to detail, black holes are anything but inactive. Their horizons curve space-time. Their gravity shapes galaxies. When fed, their surroundings can shine with ferocious intensity. Somehow, an entity that forgets almost everything about its past still manages to drive long-lived flows of energy in the present. The next step is to understand how such an object, defined by amnesia and bounded by a one-way surface, can participate in thermodynamics at all. For that, we need to ask a different kind of question, not what the black hole remembers, but how we count the hidden possibilities that remain. The hidden possibilities are there whether we name them or not. What changes is only how brutally we are willing to count, and what we accept as lost when we decide that two very different arrangements look the same. In everyday physics, we almost never track every detail. Take a sealed room filled with air. At any moment, there is a vast number of molecules rushing about, colliding, bouncing off the walls. If you somehow knew the position and velocity of each one, you could in principle predict what the room would look like in the future, down to the tiniest fluctuation. That complete specification, listing every microscopic detail, is what physicists call a microstate. It is one exact arrangement among many. But when we talk about the room in ordinary life, we do not describe microstates. We say the air has a certain temperature and pressure, perhaps a certain humidity. Those are coarse summaries. Many different microstates correspond to the same temperature and pressure. The air can be rearranged molecule by molecule in countless ways while still feeling the same to us. That coarse description is called a macrostate. Entropy is a way of counting how many microstates fit inside a single macrostate. Low entropy means only a few microscopic configurations are compatible with the large-scale conditions. High entropy means an enormous number of different microscopic stories all look the same from afar. It is a measure of hidden possibilities, not of chaos for its own sake, but of how much structure you are willing to ignore. The second law of thermodynamics, stripped to its core, says that for an isolated system, the entropy never decreases. Over time, systems tend to move from less probable macrostates to more probable ones, simply because there are more microstates that realize them. A drop of ink in water spreads out, not because it wants to, but because there are many more mixed microstates than neatly separated ones. A broken egg does not reassemble, not because the laws of motion forbid the reversal, but because the particular microstate that would correspond to the unbroken egg is unimaginably rare among all the possibilities. This is where the familiar arrow of time comes from. On the microscopic level, the equations that govern motion are mostly time-symmetric. Run them backward, and they still make sense. On the macroscopic level, the trend toward higher entropy picks out a direction. We remember the past and not the future because the past was arranged in a special, low-entropy way, and the present contains the blurred traces of that specialness. Now place a black hole into this picture. Suppose you have a hot gas confined in a box. The gas has a well-defined entropy. You can, at least in principle, Calculate how many microscopic arrangements of its molecules correspond to the observed temperature and density. If you open the box near a black hole and let the gas fall in, that entropy is no longer part of the ordinary universe. The molecules cross the event horizon and become inaccessible. If the black hole had no entropy of its own, you would have taken a state with some entropy and replaced it. From the standpoint of outside observers, with a state described by only a few numbers, the entropy outside would have gone down. If there were no compensating increase somewhere else, the total entropy of the combined system would have decreased. That would contradict the second law. This tension was noticed when physicists started to think seriously about black holes and thermodynamics. The way out is surprisingly strict. If the second law is to hold in all processes, black holes must themselves carry entropy. Their simple description in terms of mass, charge, and spin hides an enormous number of internal configurations that are not distinguishable from the outside, but must be counted in the bookkeeping. The next step is to ask what this entropy depends on. For ordinary matter, entropy is extensive. Double the volume while keeping the density and temperature fixed, and you roughly double the entropy. It scales with the amount of substance. With volume, black holes behave differently. Careful arguments, building on the geometry of space-time, suggest that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. The event horizon, recall, is the boundary beyond which no signal can escape. Its area is a geometric measure of how large that boundary is. For a simple, non-spinning black hole, the radius of the horizon grows in proportion to the mass. So the area grows in proportion to the mass squared. That means that a black hole twice as massive has 4 times the horizon area, and accordingly, 4 times the entropy. The constant of proportionality that connects area and entropy contains the Planck length, a tiny scale built from fundamental constants. The Planck length is roughly 1.6 times 10 to the minus 35 meters, far smaller than anything we can probe directly. If you divide the horizon area by the square of this length, you get a pure number that counts how many fundamental area units tile the surface, up to a factor involving Boltzmann's constant, which links entropy to probabilities. This count gives the black hole entropy. The result is staggering. A black hole with the mass of the Sun has an entropy on the order of 10 raised to the power of 77 times Boltzmann's constant. In words, that is a 1 followed by 77 zeros. By comparison, the entropy of the Sun itself, as a ball of plasma, is many orders of magnitude smaller. A much more massive black hole, like those at the centers of galaxies with millions or billions of solar masses, has an entropy so enormous that it dwarfs the entropy of all the stars in its host galaxy combined. So black holes, which outwardly seem to erase details, secretly store a tremendous amount of entropy. They do not destroy this measure of hidden possibilities. They absorb it and convert it into the area of the horizon. When matter with entropy falls in, the horizon area increases in such a way that the sum of the external entropy and the black hole entropy never decreases. In fact, there is a generalized second law that includes the horizon area as a key term. This is more than an accounting trick. It ties together 3 things that, in ordinary physics, are related but distinct: gravity, thermodynamics, and information. The area of the horizon is geometric. Entropy is thermodynamic. The idea of counting microstates is informational. In black holes, these threads are woven together. You cannot change one without affecting the others. There is also a deeper similarity between entropy and horizons. Both are about ignorance you cannot get rid of. When you describe a gas only by its temperature and pressure, you are ignoring the precise positions and velocities of all the molecules. When you describe a black hole only by its mass, charge, and spin, you are ignoring the detailed state of whatever has fallen in. In both cases, the entropy quantifies how many microscopic stories are compatible with what you know. But the kind of ignorance enforced by an event horizon is especially severe. It is not a choice. It is not that you could, with better instruments. Peek inside. The structure of spacetime forbids any information from coming out. The horizon does not merely hide the details in practice, it hides them in principle. The entropy associated with it is therefore a hard limit on what observers outside can ever recover. Here, the philosophical undercurrent is hard to avoid. We often act as if every detail could in principle be retrieved, as if loss is only temporary or practical, given enough time, enough care, enough technology. We imagine reconstructing what was forgotten. The black hole entropy story sketches a different possibility, that there are boundaries beyond which information, while perhaps preserved in some formal sense, is effectively gone to us forever. The universe may keep its own record, but it may not be written in a language we can read. Even in more familiar settings, entropy has this flavor. A cup of coffee cooling on a table exchanges heat with the surrounding air until it reaches the same temperature as the room. The process is simple, but the microscopic information about which molecule carried which bit of energy quickly becomes scattered. In theory, the combined system still follows exact laws. In practice, the information that mattered to you when the coffee was hot has dissolved into countless degrees of freedom you will never access. With black holes, the irretrievability is sharper. Once the coffee falls past the horizon, there is not even the hypothetical option of tracing the molecules. The only trace that survives in the external description is the slight increase in the area of the horizon, reflected in a small increment of entropy. All the nuance of how the coffee swirled and cooled is compressed into that single number. There is a strange comfort in thinking that nothing is truly lost, that somewhere, on scales of spacetime we cannot hope to touch, the information remains encoded. There is an equally strange chill in realizing that for any practical purpose, that difference does not matter. Entropy, whether in steam or in black holes, tells us not only about counting microstates, but about the limits of reversal. It says, here is how far you can go in trying to undo what has already been blended. Beyond this, the past is not forbidden, but staggeringly unlikely. The universe, as far as we can tell, respects a rule: total entropy never decreases. Black holes do not get an exemption. They cannot simply delete entropy from the ledger. At most, they transfer it into a form we can no longer unpack, spread across a surface whose microscopic meaning remains obscure. All of this leads to a quiet but sharp conclusion. If black holes have entropy, and if entropy and temperature are linked, as they are in all other thermodynamic systems, then black holes must have a temperature as well, however cold, however counterintuitive. They cannot be perfectly black in the thermodynamic sense. A system with temperature is a system that can, in principle, radiate. And that possibility, when carried through the mathematics, changes the story of black holes from silent endpoints into something less absolute. Temperature is a quiet admission of interaction. Even for something that seems perfectly sealed, it is a sign that the boundary is not entirely divorced from the rest of the universe. In ordinary matter, temperature has a simple picture. It is a way of talking about motion we cannot see. Molecules in a warm object move, vibrate, collide more energetically than those in a cold one. When you say a cup of tea is hot, you are saying that the microscopic degrees of freedom inside it carry, on average, more energy than those in the air around it. If two systems with different temperatures are placed in contact, energy flows between them as heat, not because they choose to share, but because there are more microscopic ways for the combined system to rearrange itself when the energy is more evenly spread out. The flow continues until they reach the same temperature. That state is called thermal equilibrium. No further net heat exchange, even though microscopic motion continues. Entropy and temperature are linked through this flow. Entropy tells you how many microscopic configurations correspond to your course. Macroscopic description. Temperature tells you how the entropy changes when you add or remove a tiny amount of energy. If adding heat increases entropy a lot, the temperature is low. If the same amount of heat changes the entropy only a little, the temperature is high. Once you accept that black holes have entropy, that link becomes unavoidable. A black hole that can be assigned an entropy must also be assigned a temperature. Not a metaphorical temperature, but a thermodynamic one, defined in the same mathematical way as for gases, solids, or radiation fields. The surprise comes when you ask, what sets that temperature? For a familiar object like a star, the temperature depends on internal nuclear reactions and energy transport mechanisms. For a black hole, there is no conventional interior in the same sense. The quantity that enters is instead something called surface gravity. Surface gravity is not gravity in the everyday sense of standing on a planet and feeling your weight. It is a measure of how much acceleration a rocket would need to hover just outside the event horizon, resisting the pull of the black hole. It encodes how strongly spacetime is curved at the horizon. In general relativity, this surface gravity plays a role analogous to that of ordinary acceleration in simple thermodynamic systems. The relation is stark. The higher the surface gravity, the higher the temperature. For the simplest, non-spinning, uncharged black hole, the surface gravity decreases as the mass increases. Combine these facts and you get an inversion that defies everyday intuition. Small black holes are hot, large black holes are cold. You can put rough magnitudes to this. Take a black hole with the mass of the Sun. The formula derived by Hawking gives a temperature on the order of a few times 10 raised to the power of -8 Kelvin. That is a tiny fraction of a degree above absolute zero. Absolute zero itself, 0 Kelvin, is the temperature at which classical motion would cease, though quantum mechanics still leaves some residual agitation. Now compare that to the temperature of the cosmic microwave background, the faint afterglow of the early universe that fills space. Measurements show that this background has a temperature of about 2.7 Kelvin, a few degrees above absolute zero. The cosmos, even in its dark emptiness, is a warm bath compared to the Hawking temperature of a stellar mass black hole. For black holes at the centers of galaxies, with masses millions to billions of times that of the Sun, the situation is even more extreme. Because the temperature scales inversely with mass, their Hawking temperature falls to values on the order of 10 raised to the power of -14 Kelvin or even lower. From the standpoint of thermal radiation, they are among the coldest objects we can meaningfully talk about. This coldness has a crucial consequence. A system immersed in a radiation bath exchanges energy with its surroundings. If it is hotter than the bath, it loses energy and cools. If it is colder, it gains energy and warms. In the current universe, where the cosmic microwave background sets a floor at around 2.7 Kelvin, astrophysical black holes, with their far lower Hawking temperatures, are colder than their environment. They are, in net, absorbers rather than emitters. They gain mass from the surrounding radiation and matter more readily than they lose it through their own faint thermal glow. The idea of black hole evaporation, in which a black hole shrinks and eventually disappears through this thermal radiation, is therefore not relevant for ordinary stellar or supermassive black holes on any timescale that means anything to us. Their predicted lifetimes, if you compute how long it would take for Hawking radiation to eat away all their mass in an otherwise empty universe, are measured in fantastically large exponents of years. For a black hole with the mass of the Sun, that lifetime is on the order of 10 raised to the power of 67 years. The universe as we see it now is only on the order of 10 raised to the power of 10 years old. The contrast is not just large, it is almost beyond comprehension. In that sense, black hole temperature does something counterintuitive to our folk picture of engines and power. We often associate higher temperature with more activity, more vigor, and shorter lifetimes. A candle flame is hot and brief. A smoldering ember is cooler and lasts longer. With black holes, pushed to the extremes of gravity and quantum theory, this pattern becomes radical. The most massive black holes, those that dominate the centers of galaxies, are the coldest and the most persistent. Their own thermal radiation is so feeble that, for now, it might as well not exist. What makes them seem perpetual is not an inexhaustible internal fire, but the opposite, an almost complete refusal to radiate. They change so slowly, through processes so gentle on cosmic scales, that for any practical imagination, they are fixed features of the universe. The engine keeps running not by burning through fuel quickly, but by barely bleeding any energy at all. Temperature, however, is still present in the equations. It appears in the same way it appears for any other thermodynamic system. It allows us to speak about black hole mechanics in the language of heat, work, and entropy. There are analogues of the usual laws of thermodynamics, rewritten in terms of horizon area, surface gravity, and mass. In these laws, the Hawking temperature plays exactly the role one would expect of an ordinary temperature. This fusion of concepts is unsettling. Gravity, in its classical form, is about geometry. Thermodynamics is about statistics of microscopic constituents. Temperature comes from counting degrees of freedom we cannot see individually. To assign a temperature to a black hole is therefore to hint that there is some underlying microscopic description, some enormous space of hidden configurations, whose coarse behavior is captured by the smooth geometry of spacetime. Yet we do not know, in detail, what those microstates are. Different approaches to quantum gravity offer different proposals, counting structures in string theory or loops of quantum geometry. But a complete, universally accepted picture is still missing. The temperature is there before the interpretation. The universe behaves as if the surface of the black hole carries countless unseen degrees of freedom, even if we cannot yet write down all of them. From a more personal angle, there is a quiet irony here. We live in a world where warmth and cold carry emotional weight. Warmth evokes comfort, presence, life. Cold suggests distance, indifference, an approach to emptiness. Black holes invert that symbolism. Their deepest indifference is tied to an almost perfect coldness. Yet that coldness coexists with the ability to drive some of the brightest phenomena in the universe when matter falls toward them. Their temperature is real, but hopelessly detached from any sensation we can share. The phrase, "the coldest objects that are still hot," is not a contradiction. It is a reminder that temperature is not about our senses, but about the structure of physical law. Even an object that seems maximally dark and simple, defined by a horizon that hides everything inside, cannot escape the logic that binds entropy to temperature and temperature to radiation. The connection is weak for large black holes, but it is not zero. And that non-zero value, that faint, almost theoretical warmth, is enough to open the next door. If a black hole has a temperature, however tiny, it must, at least in principle, emit radiation. To understand how an object from which nothing can classically escape can still glow at all, we have to bring quantum fluctuations of what we call empty space into the story, and look more carefully at what the horizon does to them. The fluctuations are always there, whether we pay attention to them or not. Calling something empty does not make it still. In quantum theory, emptiness is noisy. In classical physics, a vacuum is simple. Remove all matter, Remove all radiation, and you are left with nothing. No particles, no fields doing anything interesting, just a flat, silent stage. Quantum field theory replaces that picture with something less comforting. Even what we call empty space is filled with fields, and those fields are never completely at rest. A field, in this context, is not a patch of grass, but a quantity defined at every point in space and time. The electromagnetic field tells you what electric and magnetic effects would be felt if a charged particle passed through. Other fields underlie electrons, quarks, neutrinos. In quantum theory, these fields have a lowest energy state, the vacuum. But that state is not rigid. Because of the uncertainty principle, you cannot have both the energy and the value of the field fixed with perfect precision. There are always small, temporary fluctuations. One way to picture these fluctuations is to imagine brief appearances of particle pairs. A particle and its antiparticles spring into existence, borrow energy from the vacuum, then annihilate and give that energy back, all within a time so short that the rules of quantum uncertainty allow it. These are often called virtual particles. They are not particles in the ordinary sense you could catch in a detector. But the picture gives an intuition. The vacuum is restless. Most of the time, this restlessness is balanced. Pairs appear and disappear in ways that, on average, cancel out. No net flow of energy escapes. But a black hole horizon disturbs this balance. The strong curvature of spacetime near the horizon warps the quantum fields. Modes of the fields that would be symmetric in flat space become asymmetrical. The popular story goes like this. A particle pair forms just outside the horizon. One member of the pair falls into the black hole. The other escapes to infinity as real radiation. To conserve energy, the particle that falls in must carry what counts. From the perspective of distant observers, as negative energy, the black hole loses a little mass. The escaping particle is part of a slow, outward trickle of energy called Hawking radiation. As a literal mechanism, this picture is incomplete. The actual calculation uses quantum fields on the curved space-time background of the black hole and tracks how field modes evolve from the distant past to the distant future. What matters is that what looks like a vacuum state before the black hole forms does not look like a vacuum state after. Observers far away see a thermal bath of particles streaming outward. The spectrum of that radiation has the same shape as the spectrum from an ordinary hot object, with a temperature set by the surface gravity of the horizon. The result is unsettlingly precise. A black hole behaves as if it has a temperature and emits radiation accordingly, even though nothing can cross outward through the horizon in the classical picture. The radiation is not coming from inside. It is created in the quantum fields just outside the boundary, shaped by the geometry of space-time there. Because energy is conserved globally, the outward flux of radiation must be matched by a decrease in the energy, and therefore the mass, of the black hole. Over time, if nothing falls in, the black hole shrinks. As it shrinks, its surface gravity increases, which means its temperature rises. A hotter black hole radiates more strongly. The process accelerates, in the end, for a sufficiently small black hole in a cold enough universe. The evaporation could become violent, ending in a burst of high-energy radiation. For the black holes we infer in the current universe, this evaporation is essentially irrelevant. Their temperatures are far below the temperature of the cosmic microwave background. They sit in a bath of radiation that is warmer than they are. In that environment, they gain energy from the surroundings more easily than they lose it through Hawking radiation. The leak is there in principle, but drowned out in practice. Even so, the concept of the leak matters. Black holes are no longer perfectly absorbing, perfectly silent endpoints. They become thermodynamic systems that can both absorb and emit. The event horizon, which seem to mark a one-way flow of matter and information inward, also participates, through quantum effects, in a subtle outward flow of energy. The character of that outward flow is important. The Hawking radiation is thermal. That means its detailed properties depend only on the temperature, and therefore on the mass, charge, and spin of the black hole, not on the detailed composition of the things that fell in, whether the black hole once swallowed a cloud of hydrogen or a diamond planet. The radiation it emits later, in the simplest picture, looks the same. Thermal radiation is familiar from everyday life. A hot iron rod glows red, then white, because it emits a spectrum of photons determined mainly by its temperature. The microscopic motions of its atoms are chaotic. Whatever fine details once mattered about how the rod was heated are washed out in the radiation it emits. The information about those details is still present in principle, encoded in subtle correlations. But for most purposes, the glow is described entirely by a single parameter, temperature. For Hawking radiation, this simplicity is magnified. The radiation is not only thermal, it emerges from a region that, by design, shields its interior from direct scrutiny. So we get an engine that leaks energy in a way that appears to carry no accessible imprint of what powered it. The black hole loses mass, but the outgoing radiation does not, in any obvious way. Tell you what was lost. This sets up the well-known tension called the information paradox, which sharpens in later chapters. For now, it is enough to register the strange combination of features. You have an object defined from the outside by a few parameters. It has a boundary that no classical signal can cross outward. Quantum effects near that boundary create radiation that looks entirely generic. The black hole shrinks as it radiates. At some point in the far future of an empty universe, it may disappear entirely. What, then, has become of the information about everything that fell in? If it has been destroyed, then quantum mechanics, which is built on unitary evolution that preserves information, would have to be revised. If it has been preserved, it must be hidden in the fine structure of the outgoing radiation or in some more radical rethinking of spacetime near the horizon. There is no fully settled answer. The leak turns a quiet mathematical object into a stage for some of the sharpest questions we know how to ask about physics. On a more human scale, the picture is quietly disorienting. We often imagine that if we build a strong enough wall, seal a system thoroughly enough, what happens inside can be kept separate indefinitely. Hawking radiation says that when gravity and quantum theory are both taken seriously, even the most extreme wall in the universe cannot fully disconnect from its surroundings. Isolation is an approximation, not an absolute. Given enough time, the boundary itself rearranges the vacuum and lets energy escape. There is also a shift in what we mean by permanence. Before Hawking's calculation, a black hole could be treated as an ultimate sink. Matter falls in and, for all practical purposes, stays in. With Hawking radiation, permanence becomes conditional. Leave the black hole alone in a cold enough cosmos, and it will, eventually, give up its mass. The timescales dwarf anything we usually care about, but the direction is there. Inward collapse, followed by outward leakage. In that sense, the black hole is an engine that runs in two modes. While the universe is young and full of gas and stars, it mainly accretes. It grows. It shapes its surroundings through gravity and, when matter piles up outside the horizon, through intense radiation and jets, on unimaginably long timescales. After the fuel is gone and the background has cooled, it switches character. It becomes a faint ember, radiating away its own substance. The same object that once drove violent astrophysical activity ends its life as a slow, quiet leak. None of this requires intention. The engine is a byproduct of incompatible demands. The demand that gravity curves space-time in a certain way, and the demand that quantum fields cannot sit perfectly still in that curved space-time. Hawking radiation is what you get when you refuse to relax either rule. The leak is not a feature added to make the story interesting. It is the cost of taking the theories seriously all the way to the horizon. And yet, even with this leak, something is missing from the picture. The radiation tells us that black holes are thermodynamic objects, but it also strips away detail, returning energy without an obvious trace of structure. To move any further, we have to look not only at the energy that comes out, but at the way information might be encoded on the very surface that separates inside from outside. The surface that divides inside from outside is more than a line we draw on a diagram. If energy can leak while details seem to vanish, the question slowly sharpens. From where did the matter go to what happens to the story it carried? Quantum mechanics has a strict attitude towards stories. In that framework, the state of a system contains everything that can be said about it. The state evolves in time according to precise rules. Those rules are linear and reversible in the mathematical sense. Start from a given state. Let it evolve, and you can, in principle, run the evolution backward to recover exactly where you began. This property is called unitarity. It means information is never fundamentally destroyed, only rearranged and hidden. In more everyday terms, you can think of unitarity as an extreme form of bookkeeping, no matter how complicated the process. The universe does not forget which initial state led to which final state. The details may be scrambled beyond recognition, but they are still there in principle, encoded in delicate correlations between pieces of the system. Thermal radiation, on the other hand, seems to care very little about details. A hot piece of iron glows, with a spectrum determined almost entirely by its temperature. The photons streaming away do not visibly encode the history of how the iron was heated. The information is not truly gone. In principle, it lurks in tiny deviations from perfect thermality and in correlations between outgoing quanta, but if you ignore those subtleties, you treat the radiation as a mixed state, a statistical blend of possibilities, with no single clean story behind it. The information paradox emerges when you try to combine these two attitudes in the context of a black hole that forms and then evaporates through Hawking radiation. Imagine starting with a cloud of matter in a state that is pure in the quantum sense, fully specified. With all its correlations in place, the cloud collapses under gravity. A black hole forms over an immense time. In an otherwise empty and cold universe, that black hole slowly radiates its mass away and disappears. If the Hawking radiation is exactly thermal, determined only by the changing mass, charge, and spin, the final state appears to be a mixed state that depends only on those coarse parameters. Many distinct initial pure states could lead to the same pattern of radiation. The mapping from pure to mixed is not reversible. Information about the initial state seems to have been lost, not just hidden. That would violate unitarity. This is the core of the paradox. General relativity, taken literally, gives you an event horizon that hides everything inside. Quantum field theory, on that curved background, tells you that the horizon radiates in a thermal way. Quantum mechanics, taken literally, insists that the combined evolution from beginning to end must preserve information. Taken together, these three pieces do not sit comfortably. At least one of them has to give way or be modified. Different responses emphasize different parts of the picture. One naive possibility is to say that information really is destroyed in black hole evaporation, and that quantum mechanics needs to be altered. That route is costly, because the structure of quantum theory is tightly woven into much of modern physics. It also raises new problems. If information can be destroyed in one extreme situation, why not in others? And how do you keep track of when the rules change? Another possibility is to suspect that Hawking's calculation while capturing the leading behavior, misses subtle correlations in the outgoing radiation that would, if carefully accounted for, carry away the information after all. In that case, the radiation would only look thermal when you ignore those correlations. At a deeper level, it would still be part of a pure, information-preserving state. A third possibility is to question the classical picture of the horizon itself. Perhaps what we call the horizon is only an approximate notion, and when quantum gravity is treated fully, the notion of a sharp boundary breaks down in a way that allows information to escape without violating causality in the usual sense. Ideas along these lines have led to speculations about firewalls, fuzzballs, and other exotic structures, each trying to reconcile unitarity with the apparent one-way nature of the classical horizon. The paradox is not only technical, it forces us to confront two very different intuitions about loss. One says that if something falls behind an absolute boundary, cut off from all possible communication, then for us, it might as well be gone. The other says that the world is ultimately lawful in a way that does not permit erasure, only concealment. Both feel reasonable in their domains. The conflict appears when we insist on one unified description that respects both gravity and quantum theory. The holographic clue enters through the peculiar way black hole entropy scales with horizon area rather than volume. In ordinary systems, doubling the size while keeping the density similar roughly doubles the entropy. There is more space in which microscopic configurations can differ. A three-dimensional region stores information in three-dimensional fashion. For a black hole, the entropy grows with the two-dimensional area of the horizon. It is as if the number of independent degrees of freedom, the number of fundamental bits needed to describe the interior, scales, not with how much space there is inside, but with how big the boundary is. That area law suggests a strange possibility. Perhaps the true degrees of freedom of a region of spacetime can be thought of as living on its boundary surface, like data stored on a screen. This is the essence of the holographic idea. A hologram, in familiar usage, is a two-dimensional pattern that encodes a three-dimensional image. Shine light on it in the right way, and the image appears to have depth. The proposal in gravity is more radical but similar in spirit. A complete description of everything that happens in a volume of space-time might be equivalent to a description defined on a lower dimensional boundary. The boundary theory and the bulk theory would be two languages for the same underlying physics. If that is true in some precise sense, then the problem of information in black hole evaporation may have an unexpected angle. The horizon area, which grows as matter with entropy falls in, would be a measure of how many boundary degrees of freedom are being excited. The information about the interior would not need to be stored deep inside. It could be encoded, in some scrambled and non-local way, on the horizon itself, or on a more abstract boundary at infinity. In that picture, Hawking radiation would not be emitting from a structureless void. It would be coupled to the boundary degrees of freedom that carry the record of what fell in. The radiation might be approximately thermal when you look at small parts of it, but over the full evaporation process, correlations between early and late quanta could carry enough information to make the overall state pure. The paradox would then dissolve not because information is created from nothing, but because our naive separation of interior and exterior was never fundamental. Concrete realizations of holographic dualities exist in special kinds of spacetimes used as laboratories in theoretical physics. In some cases, a gravitational theory in a higher dimensional curved space is mathematically equivalent to a non-gravitational quantum field theory, living on the lower dimensional boundary of that space. Calculations that are hard on one side become easier on the other. Black holes in the bulk correspond to hot, thermal states in the boundary theory. In those examples, unitarity is manifest on the boundary side. The boundary theory evolves in a way that preserves information by construction. Because the two descriptions are equivalent, the bulk process of black hole formation and evaporation cannot truly destroy information either, even if it looks that way in a coarse description. The boundary becomes a bookkeeping device that guarantees that no story is fully erased. Of course, our real universe is not identical to those idealized spacetimes. The holographic dualities we understand best live in environments with negative cosmological constant and exact symmetries that our cosmos does not share. Still, they provide an important proof of possibility. They show that in at least some gravity theories, the tension between black holes and quantum mechanics can be resolved without giving up unitarity. The price is a profound reorganization of how we think about space, time, and locality. There is an existential echo here that is hard to ignore. On one hand, the holographic idea offers a kind of reassurance. What looks from within, like irretrievable loss, may, from a more complete perspective, be only a change of encoding. The story does not end, it moves to another surface. On the other hand, that surface may be completely inaccessible to any inhabitant of the bulk. The fact that the universe keeps a perfect record does not mean that record is available to the beings living inside the events it describes. It is a familiar pattern in a different disguise. We often suspect that more could be understood about our own lives if only we could step outside them. See them from a different vantage. Rewrite them in some higher language where contradictions dissolve. Holography offers a literal version of that move in physics. Move the description to a boundary, and some puzzles about the interior become easier. But the move is theoretical. The inhabitants of the bulk do not get to climb out and read the boundary directly. In that sense, the holographic clue sharpens, rather than softens. The original insight about engines and control, the universe may preserve information with exquisite care, may never let a bit of it truly disappear. Yet that global fidelity does not translate into local power. You cannot, as a practical observer falling toward a horizon, use holography to save yourself or to reconstruct the full past from the warm radiation drifting in from the sky. The engine runs according to rules that guarantee a kind of cosmic bookkeeping. But that bookkeeping is not designed for anyone's benefit. The information paradox remains an open arena of research. Proposals involving quantum extremal surfaces, entanglement, wedges, and so-called islands suggest that when quantum gravity is treated more carefully, the entropy of Hawking radiation over time follows a curve compatible with unitary evolution. In these pictures, parts of the black hole interior are effectively included in the description of the radiation itself. The boundary between inside and outside, once again, is less absolute than the classical horizon suggests. What does not change is the basic character of the engine. A black hole, seen through this lens, is not a void that deletes what it swallows. It is a system that shreds and re-encodes. It takes organized configurations of matter and fields and turns them into boundary data plus, eventually, a long, weak stream of radiation whose hidden correlations exhaust the ledger of what was once inside. The process is unimaginably complex, but also utterly impersonal. And while these questions about information play out near the edge of theory, something simpler and more visible is also happening around black holes, under the right conditions, when there is enough material nearby. The space just outside the horizon becomes one of the brightest places in the universe. The same object that challenges our ideas about memory and loss can, in a different regime, act as the central component of a long-lived astrophysical engine whose output spills across intergalactic space. The same object that quietly hoards information at its horizon can, in a different regime, blaze so intensely that it drowns out an entire galaxy. That is what happens when the engine is not starving, but overfed. When astronomers first noticed quasars in the middle of the 20th century, they did not look like anything special. On photographic plates, they appeared as point sources, almost indistinguishable from ordinary stars. The name itself, quasar, came from quasi-stellar radio source, a reminder that they were catalogued as star-like objects that happened, in some cases, to emit strong radio waves. What made them strange was not their appearance, but their spectra. A spectrum is what you get when you spread light out into its constituent colors or wavelengths. Like a rainbow, simple systems give simple patterns. Stars show characteristic dark lines where specific chemical elements in their atmospheres absorb certain wavelengths of light. Quasars showed similar patterns, but shifted far toward the red end of the spectrum. That redshift meant their light had been stretched by the expansion of the universe during its journey. Interpreted within general relativity and cosmology, such large redshifts placed them at enormous distances. If they were really that far away, then to appear as bright as they did in our telescopes, they had to be unimaginably luminous. A single quasar could outshine the combined output of the billions of stars in its host galaxy. Some radiate as much power as thousands of ordinary galaxies. They flicker and vary on timescales of days to months, which implies that the region producing the light cannot be larger than the distance light travels in that time. You cannot have a source the size of a galaxy changing coherently in a week. So the picture that emerged was unsettling. Somewhere in the distant universe there were compact regions, no larger than a solar system or a bit more, pouring out energy at a rate that rivaled or exceeded entire galaxies. They were small, bright, and remote. The sky, when seen in certain wavelengths, was dotted with these intense beacons. The suspicion grew that these objects were not separate species of things, but phases in the lives of galaxies. What we now call a quasar is understood as an active galactic nucleus, a galaxy whose central supermassive black hole is being vigorously fed. Many galaxies, including our own, harbor black holes at their centers, with masses ranging from millions to billions of times the mass of the Sun. Most of the time, those central black holes are quiet by cosmic standards. They may accrete a trickle of gas, but the process is slow and the emission modest. A quasar is what happens when the feeding rate surges. Galaxy mergers, inflows of gas from cosmic filaments, and internal instabilities can drive large amounts of matter toward the galactic center. Instead of falling straight in, that inflowing matter forms a rotating disk around the black hole. The disk is called an accretion disk, a flattened structure where material spirals inward, gradually losing energy and angular momentum. Friction and turbulence in the disk heat the gas to extreme temperatures. Closer to the black hole, where orbital speeds are a significant fraction of the speed of light, the heating is intense enough to produce ultraviolet and X-ray radiation. The disk becomes a luminous furnace. Above and below it, clouds of gas are ionized and driven into motion, producing the broad emission lines seen in quasar spectra. In some systems, magnetic fields thread the disk and the black hole, launching narrow, relativistic jets that punch out into intergalactic space. The crucial point is where the energy comes from. Nuclear fusion in stars converts a small fraction of mass into energy, according to Einstein's relation. Stellar fusion is efficient compared to chemical reactions, but still converts less than 1% of the available rest mass energy of the fuel. Accretion onto a black hole can be much more efficient. As matter spirals inward, it falls deeper into the gravitational well. In doing so, it can convert on the order of a few percent, or in some cases more than 10%, of its rest mass into radiation before crossing the horizon. That means that a comparatively small amount of mass, if fed steadily into the accretion disk, can power an enormous luminosity. The black hole does not need to consume its fuel in a single flash. It can sustain a high power output over millions of years, limited by how much gas is available and by feedback effects. As radiation pressure builds up, it pushes back on the infalling matter, regulating the inflow. Too much power chokes off the fuel supply. The engine finds a balance. not through planning, but through the constraints of gravity and radiation, compared to explosive events like supernovae, which release vast energy in a matter of days. Quasars are slow-burn engines. They do not peak and die quickly. A quasar phase in a galaxy can last tens of millions of years, perhaps with periods of greater and lesser activity. During that time, the central black hole can grow significantly, gaining mass and spin. The galaxy around it is altered by the outflows and radiation. Gas can be heated or blown out of the galactic center, affecting future star formation. From far away, we only see the integrated effect, a point of light, flickering slightly, whose spectrum carries the fingerprints of high-velocity gas, intense radiation, and enormous distance. It is tempting to anthropomorphize, to speak of the black hole as hungry, as the galaxy is feeding it. But the process does not require desire. It requires only that matter in the right configuration finds itself in a deep gravitational potential and has a way to dissipate energy as it falls. The phrase maximum power becomes, in this context, a description rather than a boast. Quasars represent near maximal exploitation of the available gravitational energy around a supermassive black hole, at least within the limits set by radiation pressure and the structure of the inflow. They are nature's way of running the engine hard, not in a burst, but in a sustained mode where inflow and outflow coexist. Seen this way, quasars are less like lighthouses built to guide and more like industrial accidents scaled up to cosmic proportions, flows and feedback loops that happen because nothing prevents them. Their beams do not point with intention. The jets they launch, when present, carve through their surroundings because magnetic field lines and plasma instabilities direct them that way, not because anyone has chosen a target. Yet their influence is real. They can heat the gas that would otherwise cool and form stars. They can enrich and stir intergalactic space with particles and fields. We are used to thinking that persistent, high-power output implies design, control, purpose. Engines, in our experience, belong to someone. They are built, maintained, and directed. A quasar undermines that intuition. Its engine is a consequence of boundary conditions and physical laws. Its persistence comes from stability, not management. If the fuel stops, the emission fades. If the fuel is plentiful, the emission grows until it triggers the very processes that limit further feeding. From our small vantage point, looking across billions of light years, there is no sign that the universe values the effects of these engines. The radiation that reaches us now left its source long before Earth formed. The structures it helped shape will outlast us by stretches of time too long to picture. We can measure, model, and name, but the relationship remains one-sided. The quasar does not react to being seen. In the larger story of black holes as engines, quasars mark a regime where almost everything that can happen does. Gravity pulls matter in. Rotation organizes it into a disk. Friction and magnetic fields heat and accelerate it. Radiation and jets push matter back out. The system sustains itself for as long as supplies and balance allow. Then, gradually, the fuel wanes. The disk thins. The jets weaken. The glare subsides. The galaxy settles into a quieter phase. At the center, the black hole remains, more massive, perhaps spinning faster, waiting for whatever slow rearrangements of cosmic structure might. Someday, feed it again. The engine has not learned anything from the episode. There is no memory in the parameters it retains, beyond mass and spin. Yet the space around it is different. Gas is thinner. Stars may be fewer or distributed differently. The galaxy's future has been bent by a process that had no plan. To understand how this engine converts simple infall into such complex behavior, We have to look more closely at the disk itself, at the way matter falls not straight down but around, shedding energy and angular momentum as it spirals toward the horizon. That is where the conversion from gravitational potential into light and heat really happens. In a thin, turbulent region balanced precariously between falling in and being blown away. That thin, precarious region between falling in and being blown away is where almost all the visible work is done. When the engine looks brightest, the black hole itself is dark. The light comes from matter learning, step by step, how to let go. A useful place to start is with something deceptively simple: orbits. Imagine a small body moving around a massive one, like a planet around a star. It does not fall straight in because it has angular momentum, the rotational counterpart of ordinary momentum. Angular momentum measures how hard it is to change a spinning or orbiting motion. To make a planet drop into its star, you would need to get rid of nearly all of that angular momentum, not just its energy. Around a black hole, the same principle holds. Gas, dust, and stars drawn in by gravity rarely head straight for the horizon. They arrive with some sideways motion. That sideways motion keeps them in orbit for a while. But unlike a solid planet, a cloud of gas is made of countless particles colliding, rubbing past each other, and interacting with magnetic fields. Those interactions provide a way to move angular momentum around. Some parcels of gas give up a little and spiral inward, others gain and move outward. Accretion is the name for this slow inward drift. The term simply means growth by accumulation, bit by bit, as material falls onto an object. An accretion disk is what forms when infalling matter organizes into a flattened, rotating structure around a central mass. The disk is not a rigid plate. It is more like a series of nested rings, each at a different distance from the center, each orbiting at a different speed. Because gravity is stronger closer in, the inner parts of the disk orbit faster than the outer parts. This differential rotation is important. It stretches and twists any magnetic fields threading the gas. It also means that neighboring rings of material are trying to slide past each other. The result is shear, layers moving at different speeds rubbing together. In a fluid, shear tends to generate turbulence, a state of chaotic, swirling motion in which eddies of many sizes appear and interact. Turbulence, combined with magnetic effects, acts like an effective viscosity. Viscosity, in everyday language, is how resistant a fluid is to being sheared or stirred. Honey has high viscosity, water has low viscosity. In an accretion disk, microscopic collisions alone are not enough to transport angular momentum efficiently. But the tangled magnetic fields and turbulent flows create an effective drag between different layers of the disk. That drag allows angular momentum to be transferred outward and energy to be dissipated as heat. The energy that appears as heat in the disk does not come from a core inside the black hole. It comes from gravitational potential energy being converted as matter moves inward. Gravitational potential energy is the stored energy associated with position in a gravitational field. A stone high above the ground has more potential energy than the same stone on the floor. When you let it fall, that potential energy becomes kinetic energy, the energy of motion, and then heat and sound when it hits. In the disk, each ring of material sits at a different gravitational potential. As gas drifts from an outer orbit to a slightly inner one, it moves to a lower potential. The difference in energy between those two orbits has to go somewhere. Some of it becomes extra-orbital speed. The rest is converted into heat by the friction-like processes in the disk, step by step, as matter spirals inward through many such rings. A substantial fraction of its original rest mass energy is turned into radiation. This is what makes accretion onto a black hole such an efficient engine. You are not burning fuel in the chemical or nuclear sense. You are letting gravity do the work, gradually lowering matter into a deep well and charging a kind of radiative brake as it falls. The closer the inner edge of the disk gets to the black hole before plunging in, the larger the fraction of energy that can be extracted. Around a non-spinning black hole, the innermost stable circular orbit sits a few gravitational radii from the horizon. Around a rapidly spinning one, that stable orbit can lie much closer. The nearer you can orbit stably before crossing the point of no return, the more energy you can, in principle, radiate away. All of this happens without any solid surface. In a star, energy is generated in a core and then transported outward through layers of gas. In a black hole accretion disk, the engine is the journey, not the center. The black hole is a sink, a boundary condition. It provides the deep potential well and the one-way inner edge. But the light comes from the struggles of the matter outside to shed what it must shed in order to fall. Viewed in detail, the disk has structure. There are regions where most of the light is emitted. Often, in a relatively thin band, a few tens of gravitational radii from the black hole, there can be corona of hot plasma hovering above the main body of the disk, scattering photons to higher energies. Further out, the disk becomes cooler and thicker, and eventually blends into the more ordinary gas of the galactic nucleus. But the broad picture is consistent. Gravitational energy is tapped as material gradually trades orbital order for heat and radiation. Radiation pressure plays a crucial regulating role. Radiation is not just light, it carries momentum. When photons stream outward from a luminous region, they push on the matter they encounter. If the disk shines too brightly, the outward push on infalling gas can become strong enough to slow or even halt the inflow. There is a characteristic luminosity, often called the Eddington limit, at which the outward force of radiation on electrons in the gas balances the inward pull of gravity on the protons. If the system tries to exceed this luminosity steadily, infall becomes difficult. The result is a kind of self-regulation. Feed the disk more vigorously, and its luminosity rises. As it brightens, radiation pressure pushes back, thinning the inflow. When the supply slackens, the luminosity falls, and infall becomes easier again. The engine finds an operating point not because it seeks balance, but because imbalances trigger processes that restore a rough equilibrium. On human scales, we associate regulation with oversight and intention. We design control systems to keep reactors stable, to keep engines from tearing themselves apart. In the accretion disk, control emerges from the interplay of simple rules extended over huge ranges of scale. Gravity pulls, turbulence stirs, magnetic fields channel and reconnect, radiation pushes. There is no central authority, yet the system can sustain a remarkably steady luminosity over millions of years. Accretion disks are not always smooth and continuous. They can break into clumps, develop spirals, launch winds. Instabilities can trigger bursts of increased brightness or sudden dimming. In binary systems where a stellar mass black hole accretes from a companion star, disks can switch between states, changing their temperature and radiation patterns over timescales we can observe. These variations are a reminder that engines built by the universe are not fine-tuned machines. They are processes that sit in marginal zones between order and disorder. Technically, much of the detailed behavior is studied through numerical simulations. Supercomputers evolve the equations of magnetohydrodynamics, the theory that describes conducting fluids in the presence of magnetic fields, in full 3 dimensions. In those simulated disks, one can see the magnetorotational instability at work. That instability is a specific mechanism by which weak magnetic fields in a differentially rotating disk are amplified and create the effective viscosity needed for accretion. The name is long, but the idea is simple. When inner and outer layers of the disk are linked by magnetic field lines, their tendency to orbit at different speeds makes the linkage unstable. The inner parts lose angular momentum and fall inward. The outer parts gain and move outward. Energy is converted into heat along the way. In the larger narrative about engines and control, accretion disks emphasize a particular point. The power does not originate in a hidden core with special properties. The black hole is, in many ways, simple. The complexity that powers quasars and active nuclei lies in the flow pattern just outside the horizon, where matter negotiates between staying in orbit and surrendering to gravity. The engine is a pattern of falling, not a thing. It is easy, looking at images of glowing disks and jets, to imagine purpose. The disk looks like a structure, the jet like an output channel, but the logic runs the other way. The disk is what happens when too much angular momentum prevents direct infall, and the only available path inward involves friction, heating, and radiation. The jet is what happens when rotating plasma and magnetic fields find a configuration that can throw energy outward along the rotation axis. Nothing about the process is aimed at producing a particular effect. It is simply where the equations take matter under those conditions. If we step back, the arrangement has a quiet implication. The most powerful long-lived engines in the universe operate by consuming gradients, differences in potential, in density, in rotation. They do not create energy from nothing. They move energy from one form to another, from the deep gravitational well of a black hole to the luminous radiation of a disk and the kinetic energy of outflows. Once the gradients are exhausted, the engine fades. The fuel is not a special substance. It is the very pattern of imbalance in the surrounding matter. From within our own lives, we often seek a core, a central source from which meaning or power flows. The accretion disk story offers an alternative picture, influence emerging from how things fall together, how they rub, how they shed what they cannot keep. The core here is a horizon that says almost nothing. The engine is the restless structure around it, temporary, bright, and destined to thin out as the gradients that sustain it are spent. To follow the energy further, we have to look at how rotation and magnetic fields do more than just heat the disk. Under certain conditions, they can grab a portion of the black hole's own stored rotational energy and launch it outward in narrow streams, turning a spinning spacetime into the drive shaft of a much larger machine. Those narrow streams do not come from pipes or nozzles. They emerge from invisible structures in spacetime itself, pulled tight by rotation and threaded by magnetic fields that never ask to be part of a machine. Spin, in this context, is not a poetic word. It is angular momentum, the stored rotation of a body. For a black hole, that rotation is not the spinning of a solid surface, because there is no surface in the usual sense. Instead, the entire geometry around it is twisted. General relativity predicts that a rotating mass drags spacetime along with it. This effect is called frame dragging. A small gyroscope near a spinning black hole would have its axis slowly torqued, not because anything touches it, but because the very grid of space and time it uses as reference is being pulled around a rapidly rotating black hole. This dragging is so strong that there is a region outside the event horizon where nothing can remain truly at rest with respect to distant stars. This region is sometimes called the ergosphere. Inside it, every possible future-pointed path must rotate in the direction of the black hole's spin, even if it still has some chance to escape outward. It is a domain where rotation is compulsory. Angular momentum is a kind of stored capacity to do work. In more familiar terms, a spinning flywheel can be used to power machinery if you find a way to couple it to gears or belts. The faster it spins, the more energy is available to be extracted. The question near a black hole is how, if at all, that stored rotational energy can be tapped by the surrounding matter and fields. Magnetic fields provide the coupling. A magnetic field is a pattern in space that tells a moving charged particle which way to curve. It is produced whenever electric charges move. and it feeds back on those charges in turn. In an accretion disk, where hot plasma orbits the black hole, charges are in constant motion. Plasma is a state of matter in which electrons and ions are no longer bound into neutral atoms. So charges move freely. This motion generates magnetic fields. Those fields are dragged, twisted, and wound up by the rotation of the disk and by frame dragging near the hole. Lines of magnetic field are a visualization, not physical strings. But the image is useful. Imagine rubber bands anchored in the disk and threaded through the region near the black hole. As the disk spins, those bands get wound around the axis. The more they twist, the more tension builds. In reality, that tension corresponds to energy stored in the electromagnetic field. Under the right conditions, this twisted field can grab hold of the rotating spacetime itself. There is a subtle process described in the mathematics of relativistic magnetohydrodynamics, in which the field lines that thread the ergosphere are forced to co-rotate with the black hole. As they do, they carry away angular momentum and energy, transmitting it outward along the field lines as an electromagnetic flow. This flow is often described as a Poynting flux, a directed transport of energy carried by electric and magnetic fields rather than by bulk motion of matter alone. The result, when collimated along the rotation axis, is a jet. Not a loose spray, but a narrow, relativistic outflow in which plasma is accelerated to speeds very close to the speed of light. The word relativistic here means that the speeds are high enough that the effects of special relativity matter: time dilation, length contraction, and the increase of effective inertia with speed. In such jets, small differences in velocity and direction can have large effects on what distant observers see. The jet is the visible trace of an invisible torque. The black hole loses spin energy. The electromagnetic field gains it and passes it on to particles that are caught in its structure. Those particles spiral along the magnetic field lines, emitting radiation across a wide range of wavelengths, from radio waves to gamma rays. Far from the black hole, the jet can remain remarkably collimated, cutting through the interstellar and even intergalactic medium like a thread of high-energy plasma. From the standpoint of the engine metaphor, the rotating black hole and its magnetic environment form a power transmission system. The accretion disk provides fuel by bringing in matter and magnetic flux. The black hole's spin furnishes a reservoir of rotational energy. The magnetic field lines are the shafts and belts that couple rotation to outflow. The jet is the exhaust, carrying energy and angular momentum away. Unlike a human-built engine, there is no sharp separation between fuel, structure, and output. The same plasma that forms the disk also sustains the magnetic fields, which in turn shape the disk and launch the jets. Change the inflow pattern, and the spin of the black hole and the strength of the jets change over long times. Slow the black hole down by extracting energy, and the conditions near the horizon change as well. Everything is entangled. There is an efficiency buried in this, but it is of a particular kind. A rapidly spinning black hole can, in principle, have a significant fraction of its total mass energy stored as rotational energy. If magnetic fields are strong and well organized enough, they can extract a sizable part of that rotational energy over cosmic timescales. That energy then powers the jets and high-energy emission near the nucleus of the galaxy. Yet none of this looks like delicately tuned machinery up close. Numerical simulations of magnetized accretion flows show churning, knotting, reconnection events where magnetic field lines break and reconnect, releasing stored energy in bursts. The jets wobble, precess, and sometimes flicker out. The power transmission is robust not because each piece is carefully maintained, but because the underlying physics keeps re-establishing the conditions for coupling whenever enough plasma and magnetic flux are present. In our own technologies, Transmitting power over long distances requires care to avoid losses. We insulate cables, match impedances, choose materials. Near a black hole, the universe does not worry about losses. Whatever energy is dissipated as heat or radiation along the way simply becomes part of the broader glow of the system. What matters is only that enough structured electromagnetic flux survives to keep the jets and winds going. On larger scales, those jets carve into their surrounding. As they plow through gas in the galaxy and the space between galaxies, they inflate bubbles, drive shocks, and stir turbulence. Observations of galaxy clusters often show vast cavities in the hot intracluster gas, roughly aligned with radio-emitting jets from a central galaxy's nucleus. Those cavities, sometimes many tens of thousands of light years across, are signs of energy deposited over long periods. The power once stored as black hole spin now supports and heats gas far from the place where it was generated. It is tempting to treat this as a kind of feedback loop with intent, as if the black hole understands that too much gas cooling in the cluster core would lead to renewed accretion and handles it by sending out just enough energy to keep the gas warm. In reality, the loop closes because of basic cause and effect. When gas cools and flows inward, it feeds the disk and strengthens the jet. The strengthened jet heats and disturbs the gas, reducing the inflow. The system hovers around a state where cooling and heating roughly balance, not because there is a goal, but because departures from that state trigger responses that push it back. There is a larger echo here of the theme about control. The black hole engine, with its spin-powered transmission, can sustain formidable power outputs over immense spans of time. It can shape the evolution of entire galaxies and clusters. Yet no one steers it. The very features that allow energy to be extracted so effectively, the simplicity of the black hole, the universality of electromagnetism, the inevitability of turbulence in the disk, also ensure that the system is largely beyond fine control from any local agent. To tap into it is to ride a process that is already running, not to command it. For beings who associate power with agency, this is difficult to accept. We are used to engines serving purposes. We design them to drive vehicles, generate electricity, propel rockets. Here, the greatest power transmission system we can identify in nature arises without purpose and serves no one. It is simply what falling matter, rotation, and magnetic fields do when they are arranged in this particular extreme geometry. And still, even this impressive device is not truly endless. Spin can be drained, fuel can run out, magnetic flux can be rearranged and lost. On long enough time scales, jets fade, disks thin, and the black hole settles into a quieter state. Its spin slowed, its environment less structured. The transmission shuts down not with a decision but with the exhaustion of the gradients that made it possible. To understand why this fading is not a failure but a natural stage, we have to zoom out further, beyond individual black holes and their local environments, to the cosmic context in which they live. Only then does the word perpetual reveal its limited, carefully qualified meaning. From far enough away, even the shutting down of an engine looks less like an ending and more like a long, slow change of weather. Brightness rises, holds, then thins, while the universe itself barely seems to move. The word perpetual is dangerous here. It suggests something that never stops, a machine that, once started, runs forever. In human history, that idea has always been tied to control. If you could build such a device, you could own an endless source of power. Around quasars, the universe does something subtler. It does not build a device. It sets up conditions under which gravity, rotation, and matter can cooperate for an absurdly long time, then lets those conditions unravel on their own. A quasar is long-lived because it is continuously fed. It does not release all its energy in a single blast, the way a supernova does. Instead, gas keeps drifting inward toward the central black hole, forming and sustaining the accretion disk. As long as there is a supply of matter at the right densities and with the right angular momentum, the disk can keep radiating, and the jets, if present, can keep channeling power outward. This feeding is not gentle, and it is not steady in the way a carefully regulated machine is steady. Gas in a galaxy moves under gravity, collides, cools, and fragments. Over cosmic time, galaxies merge and interact. When two galaxies pass through each other, their stars mostly keep flying, but their gas clouds crash and pile up. These collisions can funnel large amounts of gas toward the center. The black hole there suddenly finds itself with a thick, chaotic reservoir of fuel. In the early universe, such encounters were more common. Space was denser. Galaxies were closer together. Mergers, close passages, and inflows along long cosmic filaments delivered gas to their centers more efficiently. It is in that era, a few billion years after the Big Bang, that quasars appear in great numbers. The universe was not more intentional then, it was simply more crowded. Engines turn on more easily in a room full of clutter than in an empty hall. Once the gas reaches the central region and forms a disk, another kind of balance emerges. Gravity pulls the matter inward. Radiation from the hot disk pushes outward. If too much gas attempts to fall in at once, the disk brightens, radiation pressure rises, and some of that gas is blown back, slowed, or deflected into winds. If the inflow slackens, the disk dims. Radiation pressure drops, and gas from further out can move inward more easily. This is feedback, in the physicist's sense of the word. It is not feedback as praise or criticism, but as a loop where output influences input. The luminosity of the disk and jets affects the state of the surrounding gas. That gas, in turn, determines how much new material reaches the disk. The result is a self-regulating engine that can maintain a roughly steady brightness over spans of time that make human history look instantaneous. On those timescales, millions of years are not eternity, but they are long enough that a galaxy can be reshaped. Quasar outflows can heat gas in the central regions, preventing it from cooling and condensing into new stars. They can drive winds that carry heavy elements forged in earlier generations of stars out into the wider intergalactic medium. They can inflate cavities in the gas between galaxies, transient on cosmic scales, but vast compared to any structure we inhabit. The word perpetual, read carefully, belongs to this sense of persistence. It does not mean infinite duration. It means sustained operation over time so long that, while the engine runs, almost everything else in its neighborhood must adjust to it. A quasar outlives many generations of stars. It may flicker and vary, but its presence is a background condition for entire epochs in its host galaxy. There is another reason these engines feel perpetual to us: our vantage point. Light from a distant quasar takes billions of years to reach us. By the time its photons fall into our telescopes, the phase we are seeing may already be over, or transformed. At the source, we see a slice of the past frozen in its active state. To us, it simply is. The turning on and turning off lie outside the window we are able to look through. From within that narrow window, the engine looks uncaused and unended. We learn, with effort, to reconstruct its history from clues, the properties of the host galaxy, the distribution of quasars at different distances, the statistics of their brightness. Those reconstructions tell a consistent story. Quasars rise in number, reach a peak in the middle age of the universe, then decline, nearby, in the present cosmic era. They are rare. The conditions that once routinely built and fed them have thinned. Gas has been used up to form stars. Some has been blown out by earlier feedback. The universe as a whole has expanded and cooled. Large structures like galaxy clusters have settled into shallower flows of matter. Black holes at galaxy centers still exist, often more massive than when they were young. But the torrents of fuel that once made them blaze, as quasars are less common, many have become quiet, accreting only at low rates, visible as modestly active nuclei or not at all. In that sense, Perpetual is much like eternal in mythology, less a literal statement than an admission that the timescales involved exceed the storyteller's horizon. For a creature that lives less than a century, millions of years are effectively forever. For a universe that has already aged for more than 10 billion years, they are an episode. The engine runs for as long as there is a gradient to exploit, then fades. The physics does not soften this. It does not offer a hidden reservoir that will keep the power flowing indefinitely. The energy comes from the gravitational potential of the black hole's environment and from the spin of the black hole itself. Both can be drained or flattened when gas settles into more even distributions, when mergers become rare, when black hole spins have been slowed by successive episodes of energy extraction and random mergers. The mechanisms that once sustained the quasar phase become less effective. The engine idles. There is a particular kind of disappointment in realizing that even nature's most impressive engines are temporary. It is tempting to hope that somewhere, somehow, there is a true perpetual machine, a place where power flows without cost or end. Black holes and quasars, examined closely, say something quieter. They show that immense, long-lived output is compatible with entirely ordinary rules: conservation of energy, growth of entropy, exhaustion of fuel. Nothing miraculous is required. What feels almost miraculous is the mismatch between the duration of these processes and the scales on which we live. A quasar can light up a galaxy for tens of millions of years without ever meaning to. It can alter the fates of stars not yet born and gas not yet assembled. From the point of view of any local beings that might evolve in that galaxy, the quasar would be part of the given background. Like climate or gravity, its eventual fading would not answer any question. It would simply be another change. Perpetual, in this context, becomes an invitation to adjust our sense of proportion. The universe can sustain engines whose operation spans durations far beyond our planning. Our institutions, our species, they are not models for what we might build. They do not offer us templates for control. They instead underline a quiet fact. Persistence does not require intention. Given enough matter, enough imbalance, and the right channels for energy to flow, an engine will run until it has nothing left to work with. What remains after that is not emptiness. The black hole is still there. The galaxy carries the marks of its active phase. The surrounding space holds relics of outflows, shock fronts, enriched gas. The engine has rewritten its surroundings, then gone silent, to see what kind of cost that rewriting carries. We have to look at the last piece of the story, not just how these engines run, but how they change the structure around them and what mysteries they leave unresolved even after the light has faded. The marks remain long after the engine fades. Some are written in gas and stars, others settle quietly into our sense of what the universe is willing to do, and what it is content to erase. The physical cost comes first. Jets and radiation from an active black hole do not simply shine and move on. They push, when narrow, relativistic jets leave the galactic nucleus. They slam into the gas that hangs between stars and between galaxies. They inflate bubbles, drive shockwaves, stir turbulence on scales far larger than the galaxy itself. X-ray images of galaxy clusters show great cavities carved out of hot gas, roughly aligned with radio-bright jets from their central galaxies. Those empty regions are not decorative. They are evidence that enormous amounts of energy have been injected over long stretches of time. holding that gas up against its own tendency to cool and fall inward. Cooling gas, left alone, condenses. It settles toward gravitational wells, forms dense clouds, and eventually forms stars. Heating from quasar activity interrupts this. By stirring and warming gas at the centers of galaxies and clusters, black hole engines can slow or even halt the formation of new stars in those regions. The galaxy trades a future of quiet, extended star formation for a comparatively brief episode of intense central power. We see the echo of this trade in correlations. When astronomers measure the masses of central black holes and compare them with the properties of their host galaxies, they find that bigger bulges tend to host more massive black holes. The mass of the black hole, although it sits in a volume smaller than a star in human units, tracks the total mass of stars in a region spanning thousands of light years. That link hints at a shared history. As the galaxy grew, the black hole grew, and the energy it released helped decide how that growth unfolded. On the largest scales, the cost is written into the texture of cosmic structure. Some gas remains hot and rarefied in clusters instead of cooling into galaxies. Some galaxies are quenched, their star formation suppressed, left with aging stellar populations and little fresh fuel. None of this is orchestrated. It is simply the long-term consequence of gravity drawing matter inward, and of those inner regions finding ways to throw energy back out. There is a more subtle cost. Closer to us, black hole engines quietly dismantle a comforting hierarchy. We like to imagine that complexity is upstream of power, that minds, plans, and designs are needed to sustain large, organized flows of energy. Quasars and jets show that the universe can achieve persistent, large-scale influence with very simple ingredients and no intention at all. That does not make human meanings small, but it does make them local. The cosmos can run for eons on processes that do not notice we are here. Beyond the costs we can sketch lies the part that refuses to settle. One unresolved piece lives in the past. Observations have revealed quasars shining when the universe was still very young, less than 1 billion years after the Big Bang. Their central black holes already had masses of hundreds of millions or even billions of suns. Growing such large objects from the remnants of ordinary stars at plausible feeding rates seems difficult in the time available. This has led to ideas about direct collapse, where unusually dense, metal-poor gas clouds in the early universe might skip the ordinary star phase and fall almost straight into massive black holes. Other suggestions involve episodes of extraordinarily rapid accretion, where black holes briefly consume matter at rates higher than the usual steady limit. Simulations explore these scenarios, adjusting initial conditions and physics, trying to see which paths can build big black holes fast enough without contradicting other observations. For now, there is no single agreed story. We know such engines were already running in the first few chapters of cosmic history. How exactly they were assembled remains partly opaque. Another unresolved piece lives not in the past, but in principle: the fate of information in black hole evaporation. Holographic arguments and studies of entropy in quantum gravity suggest that, when everything is properly counted, information is not truly destroyed. Even when a black hole forms and then completely evaporates, the details would be encoded in subtle quantum correlations spread between the black hole interior, the horizon, and the outgoing radiation. Yet from the point of view of any realistic observer, those correlations are beyond reach. No telescope can collect and decode every quantum of Hawking radiation over the lifetime of a black hole. No experiment can track the microscopic degrees of freedom of a horizon. So we are left with a split view. At the most fundamental level, the universe may keep a perfect ledger. At any practical level, black holes still behave like places where stories end without external trace. Both descriptions can be true at once, each in its own frame. There is a similar tension in how we imagine the future. Calculations that extend current physics forward suggest that black holes will be among the last active engines in a universe that has used up most of its easy gradients, long after bright stars have burned out. Accretion and, eventually, Hawking radiation will still be allowed, on timescales so long that ordinary language fails. Black holes will slowly evaporate, releasing their mass as a thin glow into an almost empty cosmos. From our vantage point, that forecast is almost irrelevant. We will not be there. Our descendants, if any, will not be there. And yet the picture carries a certain clarity. Even the engines that feel perpetual are folded into a larger process of dilution. The universe allows long-lived concentrations of energy and structure, but not permanent ones. Gravity clumps. Thermodynamics spreads. Over enough time, spreading wins. This is the quiet backdrop to every phrase about nature's most powerful engines. Yes, black holes and quasars operate at energies and durations far beyond our technology. Yes, they can dominate the lives of galaxies and sculpt the distribution of gas between them, but they do so without plan, without preference, and without the possibility of exemption from the same rules that govern a cooling cup of coffee. They persist only as long as there is energy to move downhill. It is easy to feel small against that. There is a temptation either to inflate our role, imagining hidden purposes and cosmic alignments, or to deflate it completely, deciding that if the universe does not care, nothing matters. The picture we have walked through suggests something narrower and perhaps more honest. Meaning is not written into the engines themselves. It appears, briefly, in creatures capable of looking at them, modeling them, and feeling something about the fact that they do not need us. Unlimited power, in this light, does not imply unlimited control. The engines we have traced are powerful precisely because they are indifferent. They do not stop when they have done enough. They do not adjust to avoid wasting energy on empty space. They run until their gradients are flat and their fuel is rearranged. Then they fall silent. Control, where it exists at all, belongs to the physics, not to any agent sitting at a console. What remains for us is not command but attention. To see black holes as engines is to admit that the universe is capable of long, steady work without intention. To see them as erasers is to admit that most structures, including our own, are temporary arrangements riding on deeper flows. Both views can coexist. Neither cancels the fact that, for a short time on a small planet, we can think about these things at all. So the next time you hear the phrase, nature's most powerful engine, you can choose a small, private response. Do not turn it into a symbol of destiny or a promise of progress. Instead, pause for a moment and picture what is actually there. A horizon that forgets. A disk that burns by falling. Jets that carve without aim. And a universe that lets them run until there is nothing left for them to do. Then decide, quietly, what kind of meaning you are willing to build in a cosmos that will never notice either way.